In question 1, we've got the number of hours of sunshine each day for the month of July at Heathrow, recorded in the grouped frequency table here. A histogram was drawn to represent this data, and the 8 to 11 group was represented by a bar of width 1.5 centimeters and a height of 8 centimeters. We're being asked to determine the dimensions of the 0 to 5 group. I will start by drawing a table of frequency, class width, and frequency density. For the 8 to 11 class, we've got a frequency of 8, and we can see that the class width given by the difference between the two class endpoints is 3, and therefore the frequency density is 8 divided by 3, which is just 8 over 3. Well, for the 0 to 5, we've got a frequency of 12, as we can see from the table, and the class width is obviously 5. So 12 divided by 5 is equal to 2.4. That's the frequency density for the 0 to 5 class. And therefore we say that to represent 3 units, we needed 1.5 centimeters. So 3 corresponds to 1.5 centimeters. So to represent 5 units, we need to determine the corresponding width. I'll call this x centimeters. And therefore we obtain that x is 5 times 1.5 over 3, which gives me an answer of 2.5, and that's centimeters. And for the height, we know that the frequency density of 8 over 3 corresponds to a height of 8 centimeters, so 8 over 3 corresponds to 8 centimeters, and therefore 2.4 will correspond to y centimeters. So y is given by 2.4 times 8 over 8 thirds, and this gives an answer of 7.2, and therefore we conclude that the width of the bar will be 2.5 centimeters, whereas the height of this bar will be equal to 7.2 centimeters. In part B, we are asked to use a calculator to estimate the mean and standard deviation of the number of hours of sunshine each day, giving our answers to 3 significant figures. So going to the frequency table here, we need to estimate each of the groups, each of the classes by their midpoints. So for the first class, I'm going to take 0 plus 5 over 2, which gives me 2.5. And then I'll do the same for the rest of the classes, 6.5, 9.5, 11.5, and 13. These will be the midpoints for each of these classes. And I'm going to go on my class width calculator. I press menu and then option 6, and I choose one variable. So in the column that says X, I'll be inputting my midpoints. So 2.5, then it's 6.5, then it's 9.5, then we've got the 11.5, and then it's the 13. So I'm just inputting the midpoints, and then I go to the right and up to input all the corresponding frequencies. We have 12, then it's 6, then it's 8, then it's 3, and finally it's 2. So once we do this, we can press option and ask for the one variable calculations. That's option 3 now, and we can see that X bar, it's the first entry, it's 6.63 to 3 significant figures, and sigma Y is 3.69. It's the sigma underscore X 3.69. So let me write this down. We've got that the mean Y bar is 6.63, and the units are hours, and the standard deviation sigma Y is 3.69, and that's also measured in hours. We are then told that the mean and standard deviation for the number of hours of daily sunshine for the same month in Herne were 5.98 hours and 4.12 hours respectively, and Thomas believes that the further south you are, the more consistent should be the number of hours of daily sunshine. We need to state, giving a reason, whether or not the calculations in part B support Thomas's belief. So let me start by reminding ourselves of the calculation. So we've got Herne and Heathrow, the mean and the standard deviation. We can see that the Heathrow has a higher mean, but the Hearn has a higher standard deviation. Remember, we're looking for consistency here, and consistency refers to the dispersion, to the spread. So I'll be using the standard deviation to justify my answer. I would also like to remind you of the map. So this is what it looks like. We've got Heathrow over here, and Hearn is further south. And we simply need to say that since Hearn is south of Heathrow but has a higher standard deviation, therefore it has less consistent hours of daily sunshine, which means that Thomas's belief is not supported. In part D, we are asked to estimate the number of days in July at Heathrow where the number of hours of sunshine is more than a standard deviation above the mean. So I will start by bringing the frequency table here. I will add the cumulative frequencies. So we started at 12. 12 plus 6 is 18, plus 8 is 26, plus 3 is 29, plus 2 is 31. Remember, we're trying to estimate the number of days where the number of hours of sunshine is more than a standard deviation above the mean. So I will be calculating y bar plus sigma y, which is 6.63 plus 3.69, which gives you an answer of 10.32. And therefore I can quickly draw this diagram here. The 10.32 is within this class here that spans from 8 to 11. So let me put the endpoints here, 8 and 11. Somewhere along the way we've got 10.32. And looking at the cumulative frequencies, we had 18 observations up to this point and 26 observations up to this point. So the endpoints with regards to the frequencies will be 18 and 26, and I'm trying to interpolate n here. So what I'll be doing the small opening over the small opening is equal to the big opening over the big opening here. So I'm just using a ratio. So I'm gonna say that 10.32 minus 8 over n minus 18 is equal to 11 minus 8 over 26 minus 18. So we've got 2.32 over n minus 18 is equal to 3 over 8. I can cross multiply to get 8 times 2.32 is 3 times n minus 18. I will expand to get 18.56 is equal to 3n minus 54, leading to 72.56 is equal to 3n. I will divide by 3 to get 24.19 to be n. Well, if n is the number of days, I'm just going to say that n is approximately 24. But remember, we're trying to find the number of days where we are more than a standard deviation above the mean. Well, 24 days we are up to 1 standard deviation above the mean. So what I simply need to do is say, therefore, my final answer is 31 minus 24. The total number of days was 31, which gives me an answer of 7 days. We then have that Helen models the number of hours of sunshine each day using a normal distribution with parameters mu to be 6.6 and sigma to be 3.7. And we need to use this model to predict the number of days when the number of hours of sunshine is more than a standard deviation above the mean. In other words, use a normal distribution to obtain an estimate for what we have estimated just before using the actual data. So I will start by writing down that y, my random variable, is the number of hours of sunshine following this particular distribution. Remember that the mu plus the standard deviation was 10.32, so we wish to calculate the probability of y being greater than 10.32. So I'll get my calculator, I press menu and then 7. We go to normal CD. We want the probability of being greater than 10.32. So for the lower, I'm going to put 10.32. And for the upper, I'm going to put something large and positive. I'm going to put 10 to the power of 9. My sigma now is 3.7 and my mu is 6.6. So this gives an answer of 0.157 So let me write this down. So 0.15735 . We are trying to predict the number of days in July. July has 31 days, so I'm gonna take this probability and multiply by 31, and this gives an answer of 4.88 days. It's okay to give a decimal, however, the mark scheme is also accepting 5 days as a valid answer. And finally, in F, we need to use our answers to part D and E to comment on the suitability of Helen's model. Well, from the data, we found an answer of 7. Here we got an answer of 4.88. What we can say is that 4.88 is not close to 7, and therefore Helen's model is not suitable. In question 2, we've got a meteorologist who is investigating the relationship between the daily mean wind speed W knots and the daily mean temperature T degrees Celsius. They believe there's a relationship between these two, so they obtain a random sample of 9 consecutive days from a town in the UK in July, showing the relevant data in this table here. They have calculated the PMCC, the product moment correlation coefficient, obtaining a value of 0.609. And we're being asked to explain why a linear regression model based on this data is unreliable on a day when the mean temperature is 24 degrees Celsius. We're looking at the data. 24 degrees Celsius is outside the range of observed data. As you can see, we have seen a lowest temperature of 13.2 and a highest temperature of 19.3. So obtaining an estimate for 24 degrees Celsius would be unreliable. So what we need to say is that 24 degrees Celsius lies outside the range of observed data, and hence the model would be unreliable. In part B, we need to state what is measured by the product moment correlation coefficient, and we know that the PMCC is measuring the linear association between two variables. We need to mention the word linear here, otherwise we will not be scoring that mark. So it measures the extent of a linear relationship, of a linear association between the two variables. In part C, we are asked to conduct a hypothesis test at the 5% level of significance to assess whether or not the PMCC is greater than 0. I will start by stating my null and my alternative. So we have H0, that rho is 0, versus H1, rho is greater than 0 at the significance level alpha of 0.05. This is a one-tail test because the question is specifying the direction. We're looking for a positive correlation greater than 0. We know we've got a total of 9 pairs of observations, so n is 9, and what we have calculated from the data is the 0.609. We need to go to the table of critical values of the PMCC in order to see the critical value we will be using in this particular test. So going to the table, we're looking on the PMCC. The row for n is 9, and we are at a significance level of 0.05. So we see the 0.5822. So we need to write that the critical value here is exactly what we have seen from the table, 0.5822. And we now need to assess whether what we have seen, the 0.609, is significant or not. One way to do this is to draw a bell-shaped curve like this. It's just for illustration purposes. We've seen a critical value of 0.5822, so anything to the right of this will be rejected. This is the critical region. We've seen the 0.609 lying clearly within the critical region. So what I have to say is that the 0.609 is greater than 0.5822, and therefore this is a significant result. So we write significant and we reject H0. However, this is not the end. We need to write a conclusion in context. So rejecting H0 simply means that there is evidence that the PMCC for the population is greater than 0. We then have that using the same 9 days allocation from the large dataset gave the mean to be 27.2, the mean temperature, and the mean wind speed was 3.5. Using our knowledge of the large data set, we need to suggest giving our reason the location that gave rise to these statistics. So looking at the mean temperature, this is considered to be quite high. So I would say the high mean temperature probably means that we're not in the UK. And then the low mean wind speed, it's probably not a coastal location. So if we just look at the maps, these are all the locations, so we have excluded all the UK locations. They are out of the way. We have said that it's probably not a coastal location, and Jacksonville and Perth are close to the sea, so we are only left with Beijing. So we would probably give our best guess to be Beijing. In question 3, we've got the machine cutting strips of metal. The length is capital L centimeters following a normal distribution with sigma being 0.5. Anything less than 49 centimeters or greater than 50.75 centimeters cannot be used. And we are told that 2.5% of the cut lengths exceed 50.98 centimeters. And we need to find the probability that the randomly chosen strip of metal can be used. So let's start by saying that our capital L is the length. It follows a normal distribution with a known mean mu and the standard deviation 0.5. And we have that the probability of L greater than 50.98 is equal to 0.025. Now, because one of the parameters is unknown, I will have to use standardization. Before I do that, I would like to convert the greater than into a less than. So if the probability of being greater than 50.98 is 0.025, this simply means that the probability that L is less than 50.98 should be equal to 0.975. In other words, 2.5% are above the 50.98 mark and 97.5% are below. I will now standardize. So we go into Z by deducting the mu and dividing by the standard deviation, which we know to be 0.5, and this is 0.975. So I'm gonna use my calculator here. So I press menu, option 7, and it's the inverse normal. So my area is 0.975. My sigma is 1 and my mu is 0. This will give me the value. So 50.98 minus mu over 0.5 is equal to 1.95996 ... And I can actually store this value on A. So I just press store and A. And therefore, I can now rearrange into 50.98 minus mu is 0.5A, leading to 50.98 minus 0.5A being mu. Going back on the calculator, I'm going to do 50.98 minus 0.5A, and this gives an answer of 50.00. So I'm giving answers to 3SF, so mu is 50.0. Now that we have found mu, we can proceed. We want to find the probability that the randomly chosen strip of metal can be used. So if I draw my bell-shaped curve, I know that anything below 49 or above 50.75 cannot be used. So the probability that it can actually be used is simply the probability I'm between these two. So this is the probability I'm between 49 and 50.75. Remember, I've got both the value of mu and sigma, so I can go back to my calculator. I press menu, option 7 again, it's normal CD. I'm between 49 and 50.75. My sigma is 0.5, and my mu was found to be 50.0. So this gives an answer of 0.9104. I'm quoting answers to 40p always, so 0.9104. We then have that 10 strips of metal are selected at random, and what's the probability that fewer than 4 of these strips cannot be used? So we've got a new random variable here. I'll call it x to be the number of strips that cannot be used. Now, as I check each of these strips, it will either be possible to be used or not. So this is a binomial random variable. I've got 10 such strips to be tested. So n is 10, so this is binomial 10. And the probability of success, the probability that it cannot be used, is 1 minus 0.9104. And I want to find the probability of x less than 4, which is the probability of x less than or equal to 3. So if I go back to my calculator, the 0.9104 was the probability that it could be used. I will store this on B, and therefore I've got a B here. I press menu, it's option 7, and we go down and we choose binomial CD. Option 2, variable, we put x to be 3, we put n to be 10, and we put p to be 1 minus the b. This way I maintain full accuracy throughout. I press the equal sign and I get 0.9913, which is the answer to part B. We now have a second machine cutting strips of metal of length x centimeters. X follows normal distribution with the sigma being 0.6. We collected a random sample of 15 such strips and we have found a mean of 50.4 centimeters. We need to assess at the 1% level of significance whether or not the mean length is greater than 50.1 centimeters. So this is a hypothesis test on mu. So my null hypothesis says that mu is 50.1, whereas my alternative is a one-tailed test suggesting that mu is greater than 50.1, and we are working at the 1% level of significance. We know that sigma is 0.6 and the number of observations is 15, and under h naught, meaning that if h naught is indeed true, then the sample mean x bar follows a normal distribution with mean 50.1 and a variance 0.6 squared over 15. This is the sigma squared over n. We need to find the probability of x bar being greater than 50.4. The 50.4 was observed. So I'm going to go to my calculator. I press menu. It's option 7. We go for normal CD. My lower is 50.4. My upper is something large and positive, so maybe 10 to the 9. My sigma is the square root of 0.6 squared divided by 15. And my mu is the 50.1. So this gives an answer of 0.0264. which is greater than 0.01, and therefore we have not seen something extreme. We therefore say not significant, do not reject h naught, and we need a conclusion in context. There is no evidence that the mean length of all the strips is greater than 50.1 centimeters. If you say no evidence that the length and you don't mention the word mean, you will be penalized, so be extra cautious here. You need to include the word mean. Alternatively, we could have followed a critical regional approach. We're working at the 1% level, so I could find the critical value associated at that level. So we've got the probability of x bar greater than c to be 0.01. Remember, we inherit the direction from the alternative hypothesis. This means that the probability of x bar being less than c is 0.99. I can go on my calculator, I press menu, 7, inverse normal, my area is 0.99. The parameters sigma and mu are still the ones I've inputted just before. So this gives 50.46, so C is 50.46, and we therefore conclude that the critical region is anything greater than this, so the critical region is x bar greater than 50.46. And all we need to say is that 50.4 does not lie within the critical region, so this means that we are looking at the non-significant result. We do not reject H0, and we have the same conclusion, no evidence that the mean length of all the strips is greater than 50.1 centimeters. In question 4, we've got the probability of event A being 0.35, the probability of B is 0.45, and the probability of their intersection is 0.13. And we need to find the probability of A dash given B dash. Well, it makes sense to draw a Venn diagram here just to illustrate everything that we know. So we've got two sets, A and B. Let's start with the fact that their intersection is 0.13. Now the probability of A, so all of this is 0.35. So it means that the only A part should be 0.22, found by doing 0.35 minus 0.13. And the only B part here must be 0.32. Now, if I add these three numbers together and deduct from 1, I find that the outside should be 0.33. And we're being asked to find the probability of A dash given B dash. So we know for sure that we are outside of B. Outside of B means the only A or the totally outside region here. And we are wondering what's the probability that I'm also outside of A, which is this part here. So my numerator is 0.33, and my denominator is what I have ticked, so the 0.22 plus the 0.33, which gives an answer of 0.6. We are then told to explain why the events A and B are not independent. So what we could have said is that the probability of A dash, so the probability I'm outside of A, is the 0.32 plus the 0.33, which gives an answer of 0.65, which is not equal to the probability of A dash given B dash, which is equal to 0.6. Since these two are not equal, we conclude that A and B are not independent, because if they were independent, then the occurrence of B dash would have not changed the probability of A dash happening, and therefore these two would have been the same. The fact that they are not the same means there is some dependency between events A dash and B dash, so between events A and B, and therefore the two events are not independent. Now, alternatively, we could have said that if they are independent, this means that the probability of A intersection B is equal to the probability of A times the probability of B. We know that the probability of A intersection B is equal to 0.13. Now, the probability of A times the probability of B can be calculated by multiplying the 0.35 with a 0.45. And this gives an answer of 0.1575, and we can compare the two, and we say that since the probability of A intersection B is not equal to the probability of A times the probability of B, then A and B are not independent. We then have a third event, C, such that the probability of C is 0.2. The events A and C are mutually exclusive. This means that on the Venn diagram they would appear as disjoint circles, and the events B and C are statistically independent. And we need to draw a Venn diagram illustrating events A, B, and C together with the associated probabilities. So mutually exclusive means that probability of A intersection C is 0. Statistically independent means that the probability of B intersection C is simply being given by the probability of B times the probability of C, which is 0.45 times 0.2, which gives an answer of 0.09. I can then proceed into drawing my Venn diagram. We know that the A intersection B part is 0.13, the only A part is 0.22, the probability of B intersection C is 0.09. Since all of C was 0.2, it means that the only C part is 0.11, and we knew the probability of B was 0.45, so if I deduct the 0.13 and the 0.09, I get 0.23 for the only B part, and if I add all of these and deduct from 1, I get that outside it's 0.22, and that's the complete Venn diagram. Part D, I need to find the probability of B union C and all of it dash. So probability of B union C dash means outside of B union C. Well, B union C means B or C or both, so all of these that I'm shading, and I want to be outside of this, so I simply want the 0.22, the only A part, or the 0.22, the outside region. So 0.22 plus 0.22 is 0.44. In question 5, we've got a company selling seeds, claiming that 55% of it will germinate, and we need to write down a reason why the company should not justify their claim by testing all the pea seeds they produced. Well, in statistics, this would be a census, and of course, in this case, it's not advisable because testing all pea seeds will lead to no seeds left to sell. We then have a random selection of the pea seeds planted in 10 trays with 24 seeds in each tray, and assuming that the claim by the company is indeed correct, we need to calculate the probability that in at least half of the trays we've got 15 or more of the seeds germinating. So I will start by focusing on a single tray. I will call my random variable x to be the number of seeds that germinate. Obviously this is binomial because each seed may or may not germinate. We've got 24 seeds, so the n parameter is 24, and the probability of success, the probability of germinating, is 0.55 because I'm assuming that the company's claim is correct. We need to find that in a single tray we've got at least 15 seeds germinating, so probability of x greater than or equal to 15 is 1 minus the probability of x less than or equal to 14. I'm gonna go on my calculator, it's menu, option 7. We go down to binomial CD, option 1. We choose two variables. Our x is 14, our n is 24, and our p is 0.55. So this will give us the probability we are after. It's 0.70087. So we've got 1 minus 0.70087 ... So I go back to the standard menu. I do 1 minus the ans, which is the answer we just obtained. So this is 0.2991. Now be careful here. This is not the final answer. It's actually a value that I will be using in order to get to the final answer. So I'm going to store this on A, and I'm just going to write an A here. And I'm going to focus now on the trays. I'm going to introduce a new variable y, which is the number of trays with 15 or more seeds that germinate. Now, we can classify each tray as having 15 or more seeds that germinate or not. So this is yet another binomial random variable with parameter n being 10 and probability of success being the 0.2991 to the A we obtain here. We want the probability of at least 5 of them having 15 or more seeds that germinate. So the probability of y being greater than or equal to 5, which is 1 minus the probability of y less than or equal to 4. So I'm going to go to my calculator once more. I'm going to press menu, 7. We go down to binomial CD. We choose variable. Our x is 4. Our n is 10. And our p is simply the value for A we've stored. There it is, the 0.2991. I press the equal sign. I get the 0.8512. So this is 1 minus 0.8512, which gives a final answer of 0.1488. In part C, we need to write down the two conditions under which the normal distribution may be used as an approximation to the binomial distribution. This is a standard question. The two conditions are a large value for n and p being close to 0.5. We now have a random sample of 240 pea seeds planted. 150 of these actually germinated, and assuming the company's claim is correct, we need to use a normal approximation to find the probability that at least 150 pea seeds will germinate. So we start, the original distribution is binomial with n being 240 and p being 0.55. I will calculate the mean and the variance of this. So mu is NP, which is 240 times the 0.55, which gives an answer of 132, and sigma squared is NP1 minus P, which is 240 times 0.55 times 0.45, and this gives an answer of 59.4. These will be the parameters for the approximating distribution, the normal distribution. So I'm saying that x will be approximated by a random variable t that follows normal distribution with mean 132 and variance sigma squared being 59.4. And we've been asked to estimate the probability of x being greater than or equal to 150. Well, we know that the x, the binomial distribution, is a discrete distribution, whereas the approximating distribution, the normal distribution, is a continuous distribution, and therefore we need to apply a continuity correction. So we need to add or subtract the 0.5. Well, one way we can do this is to write this statement as a strict inequality. So being greater than or equal to 150 is exactly the same as being strictly greater than 149, and therefore I take the midpoint of the 150 and the 149, so this will be approximated by the probability of t greater than 149.5. So I'm gonna go on my calculator, it's menu 7, I choose the normal CD, I want to be greater than 149.5, my upper will be 10 to the 9, something large and positive. My sigma is the square root of 59.4, whereas the mu is 132. This gives an answer of 0.01158, and that's the answer to part D. In part D, we need to use the answer to part D to comment on whether or not the proportion of the company's pea seeds that germinate is different from the company's claim of 55%. Well, we found that the probability of x being greater than or equal to 150 is 0.01158. It's actually a small probability, and all of this was calculated based on the assumption that the probability of germinating was 0.55, so assuming that the company's claim is correct. However, the fact that we obtain a small probability probably means that the claim is not supported. So what you need to say is that since the probability we just found is very small, then the company's claim of 55% is not supported.